Now let's talk about crystallization. Crystallization, so in a semi-crystalline polymer sample, we have amorphous domains and crystalline domains, and they have different thermal and mechanical properties. The amorphous domains are going to be less dense than the crystalline domains because they have less than saturated van der Waals contacts with the nearby molecules. Crystalline domains are going to be more dense because the molecules are going to be closer packed together. Remember, we have different thermal transitions that describe the amorphous domains and the crystalline domains. We have the glass transition temperature for the amorphous domains, where it goes from a plate of frozen spaghetti to a plate of thawed or cooked spaghetti, but not frozen. Then we have the crystalline domains, which undergo a crystallization temperature and a melting temperature. So today we'll talk a little bit about what are the characteristics that describe the thermodynamics of crystallization, what are the time scales and the temperatures, and also a little bit about crystalline microstructures. Then for the rest of the week, we will talk about we'll finish up crystallization, then talk about the glassy state and the glass transition. Okay, so in the crystalline state, we have a delta G of crystallization of delta H of crystallization minus T delta S of crystallization. And we know that, that the delta S term is going to be going from a melt to a crystallite will be positive delta S or negative delta S? Negative delta S. Because you're confining the chain. So the key is how to make delta H large. Large and in charge, negative. So what do we need? What are our needs? We need symmetrical chains and order. Remember that atactic polyolefins don't form crystallites, but syndiotactic and isotactic do. So we need symmetry, order, and what this allows is close packing of chains to maximize the van der Waals interactions so the van der Waals energy goes as 1 over r to the 6th. So if you're really close, you have very strong van der Waals interactions. You get even just a little bit farther away and the van der Waals energy goes down a lot. So the strongest interactions are formed, even if you have a solid amorphous material, there's a big driving force thermodynamically, at least enthalpically, to go to the crystalline phase. The other thing that helps is specific intermolecular forces. To stabilize the alignment and for example, that could be hydrogen bonding. That you might have between adjacent chains of, say, a polyisocyanate, for example, as in this case. And you must have You must have sufficient molecular motion to allow the chains to be recruited to the crystalline domains, but not too much, because then they're just going to leave again. So you must have sufficient molecular motion So how do you judge molecular motion? But by temperature. So sufficient means greater than about 30 degrees past the glass transition temperature, but not too much. If you are too close to the melting temperature, the chains will have too much energy, too much thermal energy, and they're not going to be satisfied being immobilized in the crystallite. Yeah.
So symmetry is just for close packing of molecules,
Mm-hmm.
right? So it just has to do with the structure in itself.
Yeah, so symmetry non-randomness in the molecular structure. If you have randomness in the molecular structure, you're much less likely to get crystallization. Yeah.
Question on these temperature ranges. I assume these are general trends across different types of polymers and so on.
Yeah.
Do we usually see a gap between glass and melting temperatures of more than 40 degrees?
Yes. So the question is, do we usually see temperature differences between the TG and the TM of more than 40 degrees? The answer is yes. But these are just rough rules of thumb. What can impede crystallization? Crystallization can be impeded by actually molecular weights that are too long, too high. Crystallization impeded by too high molecular weights because of entanglements. So an entanglement is the intersection of polymers that can't pass through each other, like when one loops around another and they can't easily escape. So crystallization is slowed down by molecular weights that are too high. So crystallization has two stages: nucleation and growth. So we have nucleation. So this is order stimulated by intermolecular forces. And you could have a nucleation event triggered by thermal fluctuations and local increases in density, where you have just the right local increase in density where, boom, there's a crystal, and then chains are recruited to that. But also by the presence of impurities. Impurities and, say, sidewalls of the reaction vessel. Has anybody ever seen the experiment where you take a super smooth glass flask and you have it filled with deionized water, and you have it cooled to well below 0 degrees C. You pull it out gently, and it's still liquid water even though it's below 0 C. But because it's in a very smooth flask and it's deionized, there are no nucleation sites, or very low density of nucleation sites. So actually, even though it's super cooled, it's not ice yet. But then if you give it a shake, so you give it density fluctuations, so you give it density fluctuations, and automatically the whole thing just crystallizes. So I'm sure there are YouTube demonstrations of this effect. So let's say thermal and density fluctuations give you crystallites. And the second process, once you nucleate, is growth of the crystals. And this is recruiting of other chains to the nucleus, but it's in competition with redispersion of those chains. Nucleation in competition with redispersion. So if we look at the growth rate of crystallites versus temperature, and this will be for isotactic polystyrene. So the temperature and the growth rate for isotactic polystyrene. Is it all right if I call polystyrene PS? And this is the growth rate in the radius in units of microns per minute. I'm not actually going to draw any growth rate here. And then we have temperature in Kelvin down here, 390, 410, 430, 440, 450, 470, 490. What we get is the greatest rate. So as we have a melt, so we have isotactic PS, we melt it well past TM, which will be around 500. And as we cool it down, we have enough energy to recruit chains to the crystallites, but not so much thermal energy that they just leave again. And then there's a peak here, and then as we get too cold, there's not enough thermal energy anymore, and the growth rate goes down. So on the way up, we have increasing melt viscosity, which permits the stabilization of the crystallites. So it facilitates formation of nuclei and recruitment of chains to existing nuclei. And as we get too cold, so the TG of isotactic polystyrene is around 370. Of course, I'm just sketching this, but TG is around here. So crystallization, again, doesn't really start until a little bit above TG, like 30 degrees. If you get too cold, the thermal motion is too small to recruit chains. Thermal motion too slow, weak to recruit chains to the crystallites. So if you just hold the sample at the crystallization temperature for long enough, it's going to become 100% crystalline, right? No, it doesn't actually become 100% crystalline. No real polymer system ever does, unless it's such a small sample of monodispersed molecules, like a protein or something, that actually does form completely crystalline solids. But the reason it doesn't is because you're always going to have polydispersity. You're always going to have some inequality between chain lengths. And if you have even one chain that's not as long as all the others, then what do the chains do at the end groups of that smaller chain? They have to work around it and disrupt the crystal structure. Also, if you have any amount of branching or randomness, also end groups and initiator fragments, if they're not incorporated in exactly the same spot, then that area of the polymer, that region of the polymer can't, by definition, be crystalline because there's this irregular group. It also depends, the crystallization kinetics also depends on thermal history. So if you have a sample which has small crystallites in it that you obtained by quenching a sample from the melt very quickly, so there's not time to achieve large crystallites, then small crystallites actually melt at lower temperatures than larger crystallites. So you have a broadening of the melting temperature, and that's due to a size confinement effect. So in nanostructures, and these could be metallic nanowires or thin films of metals or polymers or crystallites of a solid polymer chain, it's easier to overcome the activation energy to pull chains out if there's a lot of surface area to volume than there is for a larger crystallite that approaches bulk dimensions. So with dimensions of 100 nanometers or less, you have what are called skin depth effects that depress the melting temperature and make it easier to melt a sample that's made of mostly small crystallites. So the TC and the TM are highly dependent on the morphology. So let's just write down a little bit of what we said. We think about melting. So the first thing to know about melting is that crystallization itself is usually incomplete. usually effectively always incomplete. Crystallites of different sizes melt at different rates. Melting is associated with a volume increase. That's true for most solids that in chemistry and material science that we're ever used to dealing with. Some notable exceptions, of course, are water, where melting is associated with a decrease in volume. And the melting temperature and the range over which the melting temperature exists depends on the thermal history. It can take many days of thermal annealing to achieve an optimal to achieve the maximum crystallization that a sample is capable of achieving. Yep.
What's thermal history?
Thermal history, I heated it yesterday, but not today. Or I didn't heat it yesterday and I heated it today. Or I heated it for 5 minutes instead of 10 minutes. Can take many days of annealing. Annealing means holding at a temperature above TG. It takes many days of annealing to achieve nearly complete crystallization. Branching restricts crystallization and encourages melting. Yeah.
Branching also restricts boiling, right? Branching kind of makes something more likely to be in the liquid state.
Polymers generally don't boil.
In that Hansen model you're talking about, something similar.
I have to remind myself after class exactly what context that was in. So imagine plotting the specific volume. And this is just the inverse of the density, so cubic centimeters per gram from 1 to say 1.25 versus temperature in Kelvin from 300 to 430 for polyethylene, 2 different polyethylene samples. And you have 2 samples that have different melting profiles that look like this, and another sample that looks like this. This sample is for, this curve is for a linear annealed polymer that has been annealed for a very long time. And from the book I got this from, it was annealed, these are real data, annealed for 40 days and 40 nights. And the melting temperature occurs here, but really it occurs over kind of a range, because some of the smaller crystallites will melt first, but then it's totally melted here, and then the increase in volume is linear with temperature once it's in the melt phase. This sample is the branched sample. And even if you anneal it for 40 days, it's never going to have this, this profile. So this is TM here. So what happens is that branching reduces the temperature at which the largest crystallites disappear because they're not that large to begin with. Okay, how about some thermodynamic considerations? Yeah.
So these two types of polyethylene, they had the same molecular weight in common. Was that it? But one was branched and one was not?
I don't actually know what the molecular weight was, but one is branched and one isn't. Let's say, for the sake of argument, that they do have the same molecular weight. So what do we know about melting? That it's a first-order thermodynamic process. At melting, the system, at the melting temperature, the system is in equilibrium. So at TM, TM 0 is defined as the equilibrium melting temperature. Of purely crystalline polymer. Which is ultimately impossible to attain. But just bear with me for the sake of argument. And at equilibrium, we know that, that delta G equilibrium is equal to 0, so we can say that Tm equals delta H of melting over delta S of melting. So these are purely the enthalpic change upon melting and the entropic change upon melting. So we have an idea that we know what's going to happen once the polymer chains. Looking for my notes. To the entropy once the polymer chains melt, because we know that there's, in some sense, going to be more degrees of freedom in the melt phase than there would be in the solid phase. So let's look at some real data. So the polymer melting temperature in Kelvin, delta H in joules per mole, delta S in joules per mole Kelvin. And we will consider two similar polymers at pretty much at similar molecular weights, polyethylene and polytetrafluoroethylene. Anyone remember what polytetrafluoroethylene is? Trade name? Teflon. Teflon is like polyethylene, except all of the H atoms are exchanged for fluorine atoms. Polyethylene is this. Teflon is this. Polyethylene, milk jugs. Teflon, the lining in nonstick cookware. Which one melts at a higher temperature? Teflon. Not a trick question. So let's say these particular samples melt at 410 K and 645 K. What do we know about the difference between hydrogen and fluorine? One's electronegative and one's much less electronegative. So what do we know about intermolecular forces with atoms and molecules that are electronegative? Electronegative atoms, if there's no net dipole moment, which there isn't in Teflon, in a sample of Teflon, the intermolecular forces just based on London dispersion are going to be lower or higher than for polyethylene. Lower because it's harder to deflect the electron clouds of fluorine compared to hydrogen. We know that because it's so electronegative. So therefore, since we know that delta H is a manifestation of the strength of the intermolecular forces, we expect the energy needed to break the intermolecular forces to be less here than here. Is that right? And so far, so good. Our intuition does not fail us here. But if it takes more heat to break the intermolecular forces here, then why is the melting temperature lower?
Something involving entropy.
Oh yes, something in this column that I haven't filled in yet. But what else do we know about hydrogen and, I'll introduce that rub later. The difference is because the entropy of melting is much greater for polyethylene than it is for Teflon, despite the weaker intermolecular forces as manifested in the delta H term, which is lower for Teflon than for polyethylene. So weaker intermolecular forces, but higher melting temperature due to something about this entropy term. Now, why would the entropy difference be, why would there be such an entropy difference? And it has to do with the degrees of freedom in in the solid state, or in the melt state. There are 40 carbon atoms. And then just assume that this is the same. So a crystallite of polyethylene and teflon adopts these hairpin turns. It doesn't have to be a hairpin. It could kind of go out here and then re-enter here. But in general, there are roughly 40 carbon atoms per turn in a crystallite. So in the crystalline phase, or in the solid phase, which could be largely crystalline, or 50% crystalline, say, the structure here is pretty much the same for both Teflon and PTFE. But the difference is upon melting, you get different structures. And for polyethylene, you might get this, because it's just about one of the most flexible polymers that it's possible to have, because hydrogen is so small. And then for Teflon, you might have something like that. A much lazier chain with a longer persistence length and a bigger radius of gyration. And why would this be? Anyone want to venture a guess? But if you have the notes printed out in front of you, you already know what the answer is. Yeah.
Is it because fluorine interactions with each other, it's not as flexible in any given polymer connection?
So that's mostly right. The reason is the presence of fluorine doesn't allow chains to be as flexible. But what do we know about hydrogen and fluorine? The sizes of the atoms, they're about the same. They're about the same. The difference is not the atomic radius, but the covalent radius. Because hydrogen only has one electron, it can pack closely to the carbon atom, whereas fluorine has lots of electrons and it can't pack as closely, so it actually sticks out farther, gives you a higher barrier to rotation from one dihedral angle to the next, and therefore it's going to be a more extended chain. And this goes back to our initial argument from the first day of class that the gauche to trans energy for polyethylene is about 3 kilojoules per mole. But for PTFE, it is a whopping 18 kilojoules per mole. Due to much larger covalent radius. As opposed to the atomic radius. So if you take the energy that's kind of available to affect chemical processes in the ambient environment, and that energy is often just described as KT. So we talk about how much bigger, so a process that's close to KT is going to happen readily. Process that's has an energy that's much greater than KT is a lot more difficult to achieve. So KT at room temperature, just to give you an idea. So KT per mole equals RT, and that's 2.5 kilojoules per mole. So we can see that many more of these gauche to trans states will be accessible for the case of polyethylene than they will be for PTFE. And that's why the entropy of the melt state is greater. That's why ultimately the melting temperature of polyethylene is lower than it is for PTFE, even though the intermolecular forces here are weaker here than they are over here. Yeah.
So delta E, that's the ratio or the energy it takes for it to go to gauche to trans?
It's the energy difference. So if you have energy versus dihedral angle, and then you have some function, then this is the gap we're talking about. Okay, what do these crystallites actually look like? So crystalline morphologies, they nucleate and grow radially outward. To form a structure called a spherulite. So here's nucleation. And this is just a 2D cross-section of a 3D sample, although you can actually confine crystallization into 2 dimensions, and then they're like circular lights. This is growth. And impingement. Until we have this constellation of radially symmetric spheres of crystalline material, but they're not entirely crystalline. So if you look at the growth, I should also say that if you look at one of these spherulites under cross-polarized light, you get a structure called a Maltese cross. Malta, of course, across the narrow sea. And this you get under cross-polarized light. This cross-polarized light means that there's a polarizer. If you have a light source, then the sample, then your microscope objective, then there's a polarizer above the light source in one direction, then you have the sample, then there's a polarizer below the objective in the orthogonal direction. So ordinarily you wouldn't see anything, but the Maltese cross has some anisotropy in it that rotates light partially that allows it to go through the second polarizer. And this is the structure that you see. The reason you see this structure is because each spherulite is a special snowflake Seriously, they're all different. Where each branch has its own branches, And if you look at the branches themselves, they have these crystalline morphologies with amorphous stuff in the middle, where each of these, say in the case of polyethylene, these 40 repeat units per turn show up. So the crystallites have the molecular axes perpendicular to the axis of the dendrite of the crystallite. And these structures themselves can have one of two orientations, or one of two configurations, conformations, where one is regular folding, and the other one is more like the disordered switchboard model, where you might have some adjacent reentry, but they can go in and out of the matrix anywhere they want. So this is adjacent reentry, and this is the switchboard model. The switchboard model is favored in crystallites, or in spherulites. And the adjacent reentry model, if not necessarily favored, it's more common in solution-grown crystals than it is in spherulites. So with that, I would like to thank you for your attention, and I'll see you on Wednesday.